In this work, we look at strong field enhanced ionization in molecules with emphasis on quantum interference effects.
One of the main motivations was not only to understand how quantum effects influence this phenomenon, but also to test tools from other areas such as quantum optics, which are very, very, very powerful and are underused in strong field and attosecond physics. Enhanced ionization occurs for stretched molecules in a time-dependent low-frequency field when the lower downfield center pulls the potential barrier so that the electron wave packet located upfield can tunnel more easily than it would for a single atom. A recent paper called our attention in which phase space and quasi-probability distributions were used because the authors found that there was a population transfer from one center to the other via momentum gates, and they argued that these momentum gates were the result of the non-adiabatic response of the system to the low-frequency field. However, we really had the feeling this wasn't the end of the story, and we asked the question, is this really so? Or is there something else, like for instance quantum interference or non-classical effects? We then decided to have a look at phase-space configurations, and the two key issues are the Stark saddle, formed by the joint influence of the potential and the field, and the central saddle, which is separating the downfield and the uphill centers. When the separator is defined by the two saddles are nested, there's population trapping, but for large enough internuclear distances, they open, and then enhanced ionization occurs. In previous work, we had already used Wigner quasi-probability distributions for a single center, and we did verify that it followed upon ionization the classical separatrices. There would be fringes, there would be interference. However, the overall pattern is that the Wigner probability distribution would form a tail.
So, as we can see, starting from a delocalized initial wave packet, there's already a quantum bridge connecting both centers that disobeys all barriers of phase space. And as this wave function evolves with time, we see that the quantum bridge cycles through the momentum space and periodically brings the population back towards the upfield center. Because this phenomenon also takes place for different internuclear distances, and this changes the frequency of this cyclic motion, we were wondering how this effect would happen if our initial wave packet was localized. And so when our wave packet is localized downfield, we see that indeed the quantum bridge is absent, and we only have this semi-classical escape pathway and a very, very weak ionization yield. However, when the wave packet is localized upfield, we see that after some times, the quantum bridge starts to build up, and more importantly, at a specific internuclear distance, it no longer cycles through the momentum space. So we just have this steady flow from the upfield center through the quantum bridge to the semi-classical escape pathway and to the continuum. To better understand the motion of the momentum gates, we plotted the autocorrelation functions and see that they formed a well-defined frequency, which did not match our classical estimates. Because of that, we decided to use the quantum Liouville equation to assess where in phase space the evolution of the Wigner function was non-classical. What we found was that when using a delocalized wave packet, the quantum corrections are present from the start and are strongest around the quantum bridge. In contrast, when using a initially localized wave packet, we see that the quantum corrections start out very weak and build up over time and become extremely strong around the quantum bridge. We also note that they are completely absent around the semi-classical pathway. This all shows that the quantum bridge is a highly non-classical phenomenon.
The very fact that we have quantum bridges and momentum gates for static fields actually shows that the interpretation of the momentum gates as being a response of the system to a time-dependent field is not quite complete.
So, in conclusion, enhanced ionization is due to the interplay of two qualitatively different pathways. First, we have the semi-classical escape pathway that follows the separatrix, and then we have these quantum bridges that do not follow any phase-space barriers and that have very strong quantum corrections and cycle through the momentum space. On top of that, if we now add a time-dependent field to our system, we will have the interplay between this frequency of the momentum gates and the frequency of the laser field.
So we hope you enjoyed the video and we thank you so much for watching this.